Good day everyone and welcome to our next lesson. In this lesson, we will be discussing the equations of change, particularly the continuity equation and the Navier-Stokes equation. I will also be teaching you how to derive the velocity profiles of fluid flowing through different conduits. So let's begin. For our study on the flow of fluids and momentum transport, we have to review three fundamental laws because these are very important in our study of fluid mechanics. The law of conservation of mass, Newton's second law of motion, and the first law of thermodynamics. So let's review these fundamental laws. The law of conservation of mass states that the mass in flux should be equal to the mass efflux plus accumulation if there's any. Newton's second law of motion is anchored on the equation the summation of forces is equal to mass times acceleration. And the first law of thermodynamics states that energy cannot be created nor destroyed, and it is conserved in any change or transformation. Now, for our lesson, we will be dealing with the law of conservation of mass and Newton's second law of motion in the derivation of velocity profiles of fluids. The first law of thermodynamics will be applied in your fluid mechanics course. Now, before we dive into some hardcore mathematics, let's first discuss flow fields because we basically have two ways on how we can represent the flow of a fluid. We have the Lagrangian or Lagrange's form, and we also have the Eulerian or Euler's form. Now, the main difference between these two flow fields is simply where the observer is located. In the Lagrangian form, the observer is moving along with the fluid. On the point of view of the observer, the fluid is not moving because the observer is moving along with the fluid. In contrast, in the Eulerian form, the observer is directly looking at the fluid flowing. So in the Eulerian form, the observer is stationary while he is observing the fluid moving. In our study of fluid mechanics, we will be exclusively using the Eulerian form because it's much easier to observe the flow of fluids if the observer is stationary. In that way, we can easily observe the changing of the fluid flow properties with respect to position and with respect to time. Let's begin with the continuity equation. Again, the continuity equation is a consequence of the law of conservation of mass, meaning the mass coming in should be equal to the mass coming out plus accumulation. In this equation, we have the rate of increase of mass per unit volume represented by the partial derivative of density with respect to time. This is what we call the accumulation term. And that's equal to the net rate of mass addition per unit volume by convection. So this term already being the net rate, meaning that it's already the difference between the inputs and the outputs. Now, the mathematical symbols we have here are the nabla, or the inverted del, that is in dot product with the density multiplied by the velocity vector. Now, this operation here is what we call a divergence. This means that we are to take the partial derivative of this term, density multiplied by the velocity vector, with respect to every coordinate. So, if we are on the Cartesian coordinate system, we will be taking the partial derivative of density times velocity with respect to x, with respect to y, and with respect to z. So that is what the divergence term means. Okay? And here are the versions of the continuity equation in different coordinate systems. So we have the Cartesian coordinate system, we have the cylindrical coordinate system, and the spherical coordinate system. Now, you don't have to memorize these equations, no? These equations are given in your handbook. If we take a look at the continuity equation for the Cartesian coordinate system, you see that we have here four terms, but not all of these four terms will be used in our derivation. There will be some instances wherein we can simplify this continuity equation. For instance, if our flow is steady state, meaning that there is no accumulation, the first term derivative of density with respect to time is 0. Now, if the direction of flow is through one coordinate only, let's say for example, if the flow is only through the horizontal x-axis, you can also cancel the second and third terms because there are no flows in y and z. Okay? So the techniques on how to simplify this equation is what I will be teaching you later in our derivation. We have another simplification here. When the fluid is assumed to have constant mass density rho, The continuity equation simplifies to the divergence of the velocity vector is equal to 0, meaning the density will be removed from this differentials. It will just be the partial derivative of Vx with respect to x plus the partial derivative of Vy with respect to y plus the partial derivative of Vz with respect to z is equal to 0. That's the same thing with the cylindrical and spherical coordinates. Okay? Next, let's have Newton's second law of motion. So, a direct consequence of Newton's second law of motion is what we call the momentum equation, or simply the equation of motion. Now, this is a little bit more complicated than the continuity equation. So, let's discuss every term. The first term we have here is the rate of increase of momentum per unit volume. So, this is the partial derivative of density times the velocity vector with respect to time. Again, if we are considering a steady state flow, this term becomes 0. The first term in the right side represents the rate of momentum addition by convection per unit volume. This gradient in pressure refers to the difference in pressure exerted to the different directions of a coordinate system. The next term here represents the divergence of momentum flux or shear stress tau. And the last term represents the external force on fluid per unit volume. This is mainly the external force exerted by gravity on the flowing fluid. So if this vector momentum equation is a little too much for you, don't worry because this has already been simplified for you. And we call those the Navier-Stokes equations. The Navier-Stokes equations exist in the three main coordinate systems, the Cartesian coordinate system, cylindrical, and spherical coordinate systems. I will be teaching you some techniques on how we can simplify these equations for certain systems. We are mainly using the Cartesian coordinate system if a fluid is flowing through a plate or if it is falling down a wall. These are the Navier-Stokes equations for cylindrical coordinates, and we are mainly using these equations if we are dealing with fluids flowing inside of pipes, because pipes are normally cylindrical. And finally, these are the Navier-Stokes equations for spherical coordinates. We will be dealing with these equations if we encounter a spherical fluid element that is rotating on an axis. So with that, we are ready to derive the velocity profiles of fluid flow in certain conduits using the continuity equation and the Navier-Stokes equations. Let's start with a fluid flowing inside of a tube because that is a very common system that we will repeatedly encounter. We want to use both the continuity equation and the equations of motion to come up with an equation that will describe the distribution of velocity within the fluid flowing inside of the pipe. So let's begin. Okay, let's first visualize the flow of the fluid inside the pipe. So let me draw the side view of the pipe, the fluid flowing inside of the pipe through one direction. And we know from our previous learnings that the velocity profile of a fluid flowing inside of the pipe is parabolic, wherein there is a maximum velocity existing at the center of this pipe. We will be proving this in our derived equation later. Okay? But what's important here is we need to assign the coordinates for this system. So since we are dealing with a pipe, it's a cylinder, it would be more apt if we use the cylindrical coordinate system for our solution. In the cylindrical coordinate system, the axial direction is called the z direction. And we also have two other coordinates, that's the r and the theta. The coordinate theta refers to rotational flow. So we will not be using that here because we are assuming that the fluid is not rotating inside of the pipe. What we're going to use instead is the coordinates r, or radius. What we are representing here is that the fluid is flowing along the z direction, but based on our velocity profile, it will vary on the r direction, meaning that the velocity will vary depending on its radial location. Okay? So with this, let's start with the continuity equation. We always start with the continuity equation. This is our continuity equation in cylindrical coordinates. Now, for us to be able to simplify this, we have to list down all of our assumptions for this flow. One of the most basic assumptions that we can make is first, the flow is steady state. With us assuming that the flow is steady state, what that entails is that there's no accumulation in the system and that all of the other parameters are not functions of time. So if you're assuming that the process is steady state, all of the derivatives with respect to time are automatically set equal to 0. So with that, the first term in our continuity equation is 0. And the reason behind that is because the process is steady state. Next assumption, we assume that the fluid flowing inside of the pipe is Newtonian, meaning that its viscosity is constant. Next assumption, we are assuming that the liquid inside is incompressible. Incompressible meaning the density is constant. And the last assumption that we have to make is that the velocity is unidirectional, meaning the fluid is flowing onto one direction only, and that is through the z direction. So if we are assuming that the fluid is only flowing in the z direction, that means that u sub r, or the radial component of velocity, is equal to 0, as well as u sub theta, or the rotational component of velocity, that's also equal to 0. This is what it means for a flow to be unidirectional. The velocity only retains one component. And that also greatly simplifies our continuity equation. If you take a look at the second term, 1 over r multiplied by the partial with respect to r of density times r times the radial component of velocity. Since we don't have a radial component of velocity, this is also equal to 0. The reason? We don't have a radial component of velocity. Next term, it's also 0. For the same reason, we don't have a rotational component of velocity. Because again, we assume that the flow is unidirectional. So we are only going to retain the last term, which is the partial with respect to z of density multiplied by the z component of the velocity. And that's equal to 0. So therefore, our continuity equation simplifies to density times the partial derivative of the z component of velocity with respect to the z direction is equal to 0. If you are wondering why we have factored out density, that's because we have previously assumed that the fluid flowing inside the pipe is incompressible, meaning its density is constant. Okay? So our continuity equation has simplified to this form. Now we can proceed with the Navier-Stokes equation. So let me first erase some of this, and we will only be retaining the continuity equation. These are our equations. Now you have to discern which equations are we going to use. If you take a look at the first equation and consider the components of velocity, the velocity components that we are pertaining here is the radial component of velocity. We have established earlier that for unidirectional flow, we don't have a radial component of velocity, meaning this is just 0, 0, 0, and 0. So the entire left-hand side of the equation is just 0. If you take a look at the right-hand side of the equation, we are only interested for the shear stress acting on the z direction, varying on the r direction, and that is not what is written here. So therefore, we are not going to use the first equation because the first equation deals with the velocity and the momentum flux along the radial direction. The same goes with the second equation. This deals with the velocity and the momentum flux along the rotational direction theta. So we're not going to use this second equation as well. Okay, that means that we're going to use the last equation because this pertains now to the velocity and the shear stress on the z direction. So let's use this last equation. This is now our remaining equation of motion for the z direction. Now let's try to simplify this equation. Let's start with the first term on the left-hand side of the equation. It's the partial derivative of the z components of the velocity with respect to time. Again, our first assumption is that the flow is steady state, meaning there is no variation in the properties with respect to time. So this is equal to 0. The reason is steady state. For the next term, the radial component of velocity multiplied by this differential is automatically equal to 0 because again, we don't have a radial component of the velocity. For the third term, it's the same story. It's also equal to 0 because we don't have a rotational component of velocity. For the last term on the left-hand side equation, the z component of velocity multiplied by the derivative of the z component of velocity with respect to z is also equal to 0, but not because uz is equal to 0, but because of the continuity equation. If you take a look at the continuity equation, it contains the term the derivative of the z component of velocity with respect to z is equal to 0. That means that this term is also equal to 0. The reason? Because of the continuity equation. Okay? So the last term here is not 0 because uz is equal to 0. In fact, u sub z should not be equal to 0. That's why it became 0 because of the continuity equation. Okay? Let's take a look at the right-hand side of the equation. Now, the term negative dp over dz pertains to the pressure drop that the fluid experiences as it goes down through the length of the pipe. So we don't set that to 0. We just consider this as a separate differential. If you notice, this is not a partial derivative. It's a total derivative, meaning it's a separate derivative from the rest. Let's take a look at the next terms. We have here the partial derivative with respect to r of radius multiplied by the shear stress acting on the z direction varying on the r direction. This is the term that we need because in our case here, the velocity is through the z direction, and based on the velocity profile, the velocity will vary on the r direction. So if the velocity is along the z direction and varies along the r direction, the shear stress must also be the same. It should act along the z direction and vary along the r direction. So we are retaining this term. Okay? If you take a look at the next term, 1 over r multiplied by the partial with respect to theta of the shear stress acting on the z-axis varying along the rotational axis. Our shear stress is not varying along the rotational axis because the rotational component of velocity is 0. Therefore, that component of the shear stress is also equal to 0. The reason? Because of unidirectional flow. Next term, the partial with respect to z of the shear stress acting on the z direction varying on the z direction. This is equal to 0 because of another assumption that we call fully developed flow. Under the assumption of fully developed flow, the velocity will not vary along the same direction that it acts upon. So if the velocity is through the z-axis, it will not vary along the z-axis. Okay? Meaning that the velocity at a certain value of r will be constant along the entire z. Okay? So the reason here is fully developed flow. Now, take a look at the last term, rho multiplied by g sub z. The g sub z represents the z component of the acceleration due to gravity. Now, gravity in this case does not work on the z direction. It actually works on the r direction. So therefore, g sub z is also equal to 0. So this is all about perspective. Remember, your z direction is the horizontal direction in this case. And gravity does not work on the horizontal direction. It works on the vertical direction. That's why it's 0 in this case. Okay? So what's left with our equation of motion are just these two terms. And these two terms are all we need in order to derive the velocity profile of the fluid. So let me first erase some things and then we will continue the derivation. This equation is the remnants of our equation of motion for cylindrical coordinate system. So with this, we can now start to integrate. But let me first transpose one of the terms to the other side of the equation. We now have 1 over r times the partial with respect to r of r times the shear stress varying on r acting on z is equal to negative dp over dz. Now remember, we are treating dp over dz as a constant because it is a total derivative. And then cross-multiplying, we have the partial with respect to r of r tau rz is equal to negative dp over dz times r. We can now integrate this expression in terms of r. So integrating with respect to r, we have r tau rz is equal to the constant negative dp over dz times r squared over 2 plus c1. This is our integration constant. And then dividing both sides by r, we now have tau rz is equal to negative dp over dz times r over 2 plus c1 over r. Now at this point, we first need to determine the value of c1 before we can proceed. And we can do that by setting a boundary condition. The appropriate boundary condition in this case would be to set a value of r and then determine what should be the value of tau rz for that particular value of r so that we can determine the value of c1. So let's try to use the conditions at the middle of the flow. At the middle of the flow, we represent that as r is equal to 0 based on the positioning of our coordinate system. So at r is equal to 0, tau rz has a finite value. Although we don't know the exact value, we just know that it's finite, therefore it's not 0 and it's not infinite. Okay? So it's somewhere between 0 and infinity. So it's a finite value. So if you take a look at our equation here, if we set r is equal to 0, what would happen is that the first term here, negative dp over dz times r over 2, would be equal to 0. However, for the second term, c1 divided by 0, which is our designated value of r for the first boundary condition, would result to a shear stress or momentum flux that has an infinite value because c1 over 0 would result to infinity. And for sure, we cannot have an infinite shear stress. We have determined that the shear stress should be finite at that point. Therefore, the only logical step to this is we set c1 is equal to 0. By setting the value of c1 to 0, we are eliminating this second term of our equation, and thus we are avoiding the scenario wherein the shear stress is infinite. Okay? That's why it's necessary for us to let the value of c1 be equal to 0. And with that, we are left with the equation tau rz is equal to negative dp over dz times r over 2. With this equation, we now have the shear stress profile of the flow. And basing on the characteristics of this equation, the shear stress profile is linear because the shear stress is directly proportional to the position r. So therefore, the larger the value of r, the larger your shear stress would be. And since this is a linear function, we then expect the shape of the shear stress profile to be something like this. The shear stress is minimum at the middle wherein its r is equal to 0 and its maximum at the walls of the pipe, which is at r is equal to capital R, or the radius of the pipe. This is a familiar shape. We have already discussed this previously, and we have mentioned that the shear stress is maximum for the fluid element near the solid boundary because of the no-slip boundary condition. Okay? But we cannot stop with this shear stress profile. We have to continue until we get the velocity profile because that is what we are interested about. Now, to continue, we need to substitute Newton's law of viscosity to this simplified and integrated form of the equation of motion. So for fluid flow inside a pipe, Newton's law of viscosity states that the shear stress varying on the r direction acting along the z direction is equal to negative viscosity times the derivative of the z component of velocity with respect to the position r. So we simply substitute this to our shear stress profile and we get negative mu du sub z over dr is equal to negative dp over dz times r over 2. Now, before we move forward, you might be wondering, why am I keeping the term dp over dz with a negative sign attached to it? So we are keeping dP over dz as negative because this represents the pressure drop that the fluid experiences as it flows down the pipe. And as the name suggests, pressure drop, it's supposed to be negative. So we will be keeping the negative sign beside dP over dz for the rest of our derivations. So let me erase some things and then we can continue. Okay, let's continue. Dividing both sides by negative mu, we have duz over dr is equal to negative dp over dz times negative r over 2 mu. This is now an integrable differential equation. So integrating, we have u sub z is equal to negative dp over dz times negative r squared over 4 mu plus an integration constant c2. As with our previous integration constant c1, we first have to determine the value of c2 before we can proceed. We then set up our next boundary condition number 2. Now this time, let's try to use the no-slip boundary condition. For the no-slip boundary condition, to refresh your memory, we are saying that the fluid element that is directly adjacent to the solid boundary of the conduits will move at the same velocity as the solid boundary. In this case, the fluid is moving, but the solid boundary, meaning the pipe, is stationary. Therefore, by the no-slip boundary condition, the velocity should be 0 at a position r is equal to capital R. Remember the difference between small r and capital R. Small r denotes position within the entire radial range of the pipe, while big R pertains to the actual value of the radius of the pipe. So if your position, small r, is equal to the radius of the pipe, big R, that means that you are positioned at the solid boundary itself or at the wall of the pipe itself. And that is where no slip boundary condition is applied. So again, at a position of small r is equal to the radius of the container, the velocity of the fluid there is 0. This is because of the no slip boundary condition. If you substitute these boundary conditions to our velocity profile here, what do we have? We have 0 is equal to negative dp over dz times negative capital R squared over 4 mu plus C2. We now have a value of C2 transposing to the other side. That is negative dp over dz times R squared over 4 mu. And with that value of C2, we can now substitute this back to our velocity profile. And we now have our final velocity profile. And that is u sub z is equal to negative dp over dz times negative small r squared over 4 mu plus negative dp over dz times big R squared over 4 mu. Now, since negative dp over dz is a common factor, we can factor it out and further simplify. U sub z becomes negative dp over dz times big R squared minus small r squared all over 4 mu. This is now our full velocity profile. Okay, if you will compare this to our shear stress profile, so let me write again our shear stress profile. The shear stress profile is tau rz is equal to negative dp over dz times r over 2. Shear stress profile. The shear stress profile is linear because tau is directly proportional to r, while the velocity profile is parabolic because the velocity is directly proportional to the square of the position, that is r squared. Hence, we have a parabolic velocity profile here. Okay? And with that, we have derived the velocity profile of a fluid flowing in laminar flow inside of a pipe. And with this, we can now determine our equation for the maximum velocity. As we have noted from the parabolic velocity profile, the maximum velocity, Umax, exists if our position is 0. That means that we are at the center of the pipe. So try to substitute r is equal to 0 to our velocity profile and you will get the maximum velocity. We now have Umax is equal to, if small r is equal to 0, this becomes negative dp over dz times r squared over 4 mu. This is our expression for the maximum velocity for laminar flow inside of a pipe. Okay? And this is only true if you are at the center of the pipe, that's r is equal to 0. Okay, how about the average velocity? The average velocity pertains to the observable macroscopic velocity of the fluid flowing inside of the pipe. So the average velocity is regardless of your position in the pipe. It will be taken as the average flow of the entire fluid. How do we solve for the average velocity? We use the relationship U average is equal to 1 over A times the double integral of the velocity profile UZ multiplied by the differential in area. Okay, let me first erase some of these things. So in this case, our differential in area will become r dr d theta. So it's like determining the volume of rotation of a surface, no? And then the area in 1 over A is the cross-sectional area of the pipe, and that is pi r squared. Substituting, we have the average velocity is equal to 1 over pi capital R squared, double integral of the velocity profile u sub z, that is negative dp over dz times big R squared minus small r squared over 4 mu times r times dr d theta. Now for the inner integral dr, the limits of integration will be from 0 to capital R, meaning from the center of the pipe up to one of its boundaries, and then later we will be rotating that 360 degrees to capture the entire cross-sectional area of the pipe. And then for d theta, as I have mentioned, it has to be one entire rotation. So the limits of integration will be from 0 to 2 pi. That's 2 pi radians. And to simplify our integration, I will be rewriting the velocity profile as this. We have the average velocity is equal to 1 over pi capital R squared. We will be factoring out all of the constants from our equation. So that includes negative dp over dz, the 4 mu in the denominator, as well as the capital R squared. So if we will factor that out, we now have 1 over pi r squared times the integral from 0 to 2 pi, integral from 0 to capital R of negative dp over dz times capital R squared over 4 mu times 1 minus big R squared over capital R squared times r dr d theta. And then we can now move all of the constant terms out of the integral. So r squared would cancel. We now have negative dp over dz over 4 pi mu times the integral from 0 to 2 pi times integral from 0 to r of small r minus small r cubed over big R squared dr d theta. We are now ready for integration. Okay, let's first evaluate the inner integral. The integral of r minus r cubed over r squared dr is small r squared over 2 minus small r to the fourth over 4 big R squared. Limits of integration from 0 to r d theta. Substituting big R for small r, we now have average velocity is equal to negative dp over dz over 4 pi mu times the integral from 0 to 2 pi big R squared over 2 minus big R to the fourth over 4 big R squared d theta. Take note that that is d theta. Let's continue to the other side. Let's first simplify before we proceed to the second integration. We now have the average velocity is equal to negative dp over dz over 4 pi mu times the integral from 0 to 2 pi of big R squared over 2 minus big R squared over 4 d theta. Now let's integrate with the directional position theta. We have u average is equal to negative dp over dz over 4 pi mu times r squared over 2 minus big R squared over 4 times theta. Limits from 0 to 2 pi. Substituting, we have the average velocity as negative dp over dz over 4 pi mu times r squared over 2 minus r squared over 4, 2 pi. Cancel pi. We now have the average velocity as negative dp over dz over 2 mu times, simplifying what's inside of the parenthesis, we have 4 as the denominator. 4 divided by 2 is 2, so we have 2 capital R squared minus capital R squared. Simplifying further, we have the average velocity equal to negative dp over dz over 2 mu times capital R squared over 4. Okay, multiplying, we now have the average velocity as capital R squared over 8 mu times negative dp over dz. This is our expression for the average velocity of the fluid flowing inside the pipe. Okay, let's compare this average velocity with our maximum velocity obtained earlier. If you will remember, U max is equal to R squared over 4 mu times negative dp over dz. Do you now see a relationship between the average velocity and the maximum velocity? They look very similar. They are just differing in their denominator. So what happens if I take the ratio of the average velocity and the maximum velocity? So we take average velocity over maximum velocity. Of course, the negative dp over dz will cancel. So therefore, we are left with capital R squared over 8 mu over capital R squared over 4 mu. Mu cancels, R squared cancels. We are left with the ratio average velocity over maximum velocity is equal to 1/2. That gives you an idea that the velocity of the fluid elements at the middle of the pipe is moving twice as much as the average velocity of the entire fluid. Okay? This also allows us to convert between average velocity and maximum velocity as long as it is in laminar flow. This relationship is only valid for laminar flow. So our interpretation is, if a fluid is flowing inside a pipe in laminar flow, that means that its average velocity is 1/2 of its maximum velocity. That is a very useful relationship for laminar flow. In your fluid mechanics course, this derivation of the average velocity of the fluid flowing inside of a pipe would be the starting point for what we call the Hagen-Poiseuille equation. The Hagen-Poiseuille equation describes the pressure drop of a fluid flowing inside of a length of a pipe in laminar flow. Okay, so we have derived all of these equations and all of these relationships just coming from the continuity equation and the Navier-Stokes equation. Okay, and the same will be expected from you. If you're given a physical system, you need to represent that physical system into variables that we can use to simplify the Navier-Stokes equation and continuity equation for us to be able to describe the velocity profile of the fluid flowing in that system. So that's the end of this lecture. Please watch out for other videos which will explain the derivation for other systems. That is it for the topic of equations of change. Remember, you don't have to memorize the continuity equation in different coordinate systems as well as the Navier-Stokes equations for the different coordinate systems. What you do need to know or what you do need to remember is how to simplify those equations so that we can derive velocity profiles. Okay, I'll see you in the next examples. Keep practicing and as always, keep safe.